What do you say?
We tried to make a joke.
And yes,
He looked at the chair. I'm afraid of him.
a joke in good taste. Or?
Yeah, he just looked at your chair and said, "Where's Laurent?"
Oh, good. Sorry, I can't take this.
Okay, thank you very much for coming back for our last session of the day. For Laurent Clozel, he's right here, by the way, Jim Arthur and Shahidi. There you go. Welcome. As Fredo needs to know, there he is. Okay. Invariance of the zeros of automorphic L functions by conjugation of coefficients.
Okay. Well, thank you. Of course, it's a great pleasure to be here once more since I visited Jim assiduously 40 years ago when we were achieving base change, and I had a number of occasions to return. And this is quite a great conference so far. Maybe I'll say a little more at the dinner. And by the way, I'm not sure I'm not sure I fill my contract for 60 minutes because I understand that you all have to dress for dinner and to put on your tails and so on. So if I may finish early, actually. And I have, again, two things to say. First of all, I have to thank Witek Gan and Tasho Kaleta because I'm going to use some stuff from the comparison of classical groups and GLN stuff, which of course is contained in Arthur's 2013 books. And I'll just assume you have been at those lectures because some of the material has been presented there, and I intended to assume that this was known, and really, I mean, I'm going to use things that you have heard already here. Okay, so this is for the thanks, and as for the methods, okay, as you will see, we are interested in certain rationality results, and we are being Catholic in our choices in the sense that we use, again, functoriality, as I said, with classical groups with GLN. And sometimes we have everything in Arthur's book. And sometimes we have to look at the approach to functoriality by converse theorems, okay, which has been illustrated by a lot of people. Piatetsky-Shapiro, Shahidi, Cogdell, Kim, Soudry, and I'm certainly forgetting some. But in any case, the main people, some of whom are here, I think are listed there. So we use whatever we need. And finally, I have to mention at the start that this is common work. With yes, Arnaud Crête and yeah, Olivier Taibi. And then we encountered an interesting problem about intertwining operators for Eisenstein series. And that is solved in the paper in an appendix by Valls-Burger. And also in cooperation with Taibi. Actually, as you will see in this work, with a very specific arithmetic problem, we go back to almost to the origins of the theory with Langlands and Shahidi. And sometimes we have to improve the things which are known about Eisenstein series. Okay, so first of all, let me start with a consequence of the linear conjecture. So that's, by the way, in Corvallis in whenever that was, 77, I think. So it's the second volume of the Corvallis conference. So Deligne made a fundamental conjecture on special values of motivic L functions. Okay, so I'm not going to give a lecture on motives, so I'm not going to state the conjecture in this form, but as is now well understood, actually there is a correspondence between motives and a certain type of automorphic representations of arithmetic type. And in fact, to have the most simple formulation, automorphic representations of GLN AF, where F will be a number field. So now this has been specified very rigidly. So if we have a conjecture on motives, we can, in certain cases, test it on the automorphic representations. Okay. So in fact, let me say a little more precisely what representations we are interested in. By the way, I find that this is a problem for seeing the text, so I'll try to avoid the shade. Okay. Okay. So what are those particular automorphic representations? So I'm going to consider a representation, cuspidal, representation of GLN AF. And by the way, from now on, and this is the point of some of the results, F is an arbitrary number field, okay? So these results often were already known in some particular cases, but now F is really arbitrary, okay? So suppose that pi is a cuspidal representation, and I'm going to say that pi is algebraic if for any place of F, and in fact, I do better, I take an embedding from F to C, then I have a Lagrange parameter at the Archimedean prime. The Lagrange parameter, so we have heard a lot about a local reciprocity. This is the trivial case here, is given by Z gives, so I'm in degree n, Z Pi, Z bar Qi. And here I have to assume that two things actually. I will have Pi plus Qi equal to W, so it's independent of I. It's the geometric weight of the motive, in fact. And also I want that Pi belongs to n minus 1 over 2 plus Z. Okay. Don't ask me to detail this, but this is the half shift is the half shift in coefficients of Hecke operators and forms, which was already known to Hecke. Okay. So I'm going to consider pi, which is algebraic in this sense, and also regular. I'm sorry. What is wrong? Oh, PI. Yeah. PI. I think this is correct. Yes. What? Yeah. It also says something about QI, right?
No, it's fine. It looked like an R. That's all. R is the P. Never mind.
Oh, this is.
Never mind. It's fine.
Okay. Okay. Sorry. Okay. Can you explain to me what's wrong? Not too low, not too high. Okay. Okay. But okay, so P algebraic will be called regular if, moreover, the exponents here are distinct. Okay. Is that okay if I add this here? This says that Pi is different from Pj for all ij. Okay, these are the regular algebraic representations. Now, the point of this definition was that these representations are cohomological. These algebraic regular representations are cohomological. I am not going to write it, but it means that they have GK cohomology in the sense of actually amply developed by David Vaughan. Okay, and this has the fantastic property that assume that pi is algebraic regular, and I write it as an infinite part associated to all the Archimedean places and the finite part. So this is a representation of GL n over AF, the finite adels. Then pi, of course, is supposed to be cuspidal. And if I take an arbitrary automorphism A of the complex numbers, if you believe this exists, by the way, then this implies that there exists a representation A of pi, okay, such that A of pi f finite part is equal to A of pi f. And what is this is just given by the obvious extension of scalars. A of pi f is equal to pi f of complex vector space, tensored over C and with respect to the inverse of the automorphism and C. So basically, I just move the coefficients by the automorphism. Okay. Okay. Now, if you look back at the Lean's conjecture for motives, and you know the obvious translation into cusp forms, this has the following consequence. So I should just add something more here about the Lean, actually. A motive is something relative to the number field F, but it also has coefficients E, and E will be again a number field. Now, every time you add an embedding from A to C, then there is an L function associated to M and the embedding. So call this iota, for example, and then L of M, iota, and S. And all those L functions are supposed to be nice L functions, and they are supposed to be automorphic, associated to cuspidal representations. Okay. Now, one consequence of the Lean's formula is the following. So we can say something about special values at integers. And they are going to be related when we change the embedding from E to C. Okay, so I'm not going to say more about this because I'm going to state it in the automorphic case. So the Leans conjecture for motives using the rather worn dictionary now. This implies the following. So let me continue up there. Yeah. First of all, let me correct this. The Leans conjecture is about integers, but I have to correct this. I'm going to suppose that the total degree of the L function, for example, n is even, okay, then there is a shift in the L function from the L function of the motive to the L function of the cuspidal representation. It's a 1/2 shift. It's the same 1/2 that you have here, which depends on n generally. There's a 1/2 shift, and the consequence is that we'll be interested in special values of the L function of S pi. Pi is the cuspidal representation associated to M, okay, at half integers. Or more precisely, Z translated by 1/2. That's the first thing. So this is the special values we care about, okay? And then the consequence of the linear's formalism is the following conjecture. So assume S is in 1/2 plus Z. And I assume that it's a special, well, it's special. I didn't define special values because there is a range which is allowed. I am not going to explain here because I need only a certain case. So assume that, I'm sorry, I made a mistake here. Assume S is a critical in the Lean sense. That means that the Lean says something about the special values, okay? And then L of S pi vanishes is equivalent to L of S pi, A of pi, sorry, vanishes at S. Okay. So I have made all the assumptions there. So pi here is algebraic, cuspidal, and regular. I repeat, this follows from the Lean's conjecture. Okay. In that's it's a religious question, so I don't think I'm bound to answer. Okay, so I'll say a word at the end if you want. Yeah, the Lean doesn't, I think. Okay, okay. So now we can forget everything about motives, and we look at cuspidal representations of this particular type, and note that in fact, the only special value we'll be interested is S equal to 1/2, because for the L functions we will look at, I mean, it's very well known that outside there for these translated half integers, the L function is not 0. So now we are only looking at the center of symmetry for the standard functional equation of the L function. Okay. So this is the conjecture. And of course, it also applies to Rankine L functions. where the product degree here is even. So typically we'll have pi for GL R and R even, and a rho for GLT. This is my notation, I think, yes, and T odd. That's, for example, the kind of thing we'll be interested in. Okay. Sorry. The weight? No, I never fixed the weight. There is a coefficient system, okay? I didn't want to go into the cohomology, but on the other hand, I defined algebraic representations, okay, regular algebraic representations, and the weight of the coefficient system is encoded by the Lagrange data here. Why? Why do I want what? Why do you look at the center? Oh, I'm sorry. Yes. No. Okay, I forgot something. Thanks. Okay. So from now on, I'm going to assume that pi or rho, if it comes up, is self-dual. Okay. And a generalization in the unitary case. And so now that answers your question. That implies that W is equal to 0. Thanks. So the only point we want to look at is the center of symmetry. Okay. So we consider, again, from now on, self-dual representations or unitary self-dual, but I'll get to that in a little while. Okay. So let me make some other assumptions. First of all, I assume that pi and rho, if it comes up, is a superregular. This means that in the regularity condition here, I don't want to have the distance between pi and pj has to be at least 2. So P1, say, must be larger than P2 plus 2, larger than P3 plus 2, and so on. And I'll let you finish the sequence as you want, as you need to, using the self-duality. So this is the superregularity. And I assume that pi and rho are disjoint. Okay. This is, again, a condition on the Roche types, which have to be separate in some way. I'll write it precisely a little later.
Is the second two in the string of inequality 4?
Sorry?
P3 plus 4?
Plus 4, thanks. P2, thanks, and so on, yes. So I have an interval at most 2. Okay. So now I'm going to state immediately the main theorems. So that will give me some latitude about where to end, okay? So again, I mean, thanks to Yanis's remark, the only point we have to look at is 1/2, okay, in this case. Okay, so this is the first theorem. So this is all due to Kret, Taibi, and myself. For any A in capital A, which is out of C over Q, L of 1/2 pi cross rho vanishes if and only if L of 1/2 A of pi cross A of rho is equal to 0. Okay. So that's theorem A. Okay. Now, there is an obvious consequence, which I will state because that's the one I'll try to explain in some detail. theorem B. Remember, here we have odd degree, so we can just take the trivial representation of GL1, and that tells you that if pi is superregular, remember again that pi is of even degree. For any A, then L of 1/2 and pi is equal to 0 if and only if L of 1/2 and A of pi is equal to 0. Okay. Now I want to go on to some examples which are actually more fun.
First theorem does not have a superregularity assumption.
Where, yeah, sure. So there are two assumptions. I'm going to explicitate the second one, but superregularity for both representations, and besides, they don't interfere in a way that I'm going to describe, okay? They are disjoint. So assumptions is H, like hypothesis, and this is all under H. Is that clear?
I couldn't understand why you put the assumption only in the second theorem.
Okay, well, just to remind myself, but anyway, thanks. Okay. Oh. I can hear you.
Is A of pi known to exist?
Sure, that's what I explained before. Pi is cohomological, so you can actually conjugate the scalars. Okay, that's a very old theorem of 1988, by the way. Yeah. And by the way, then A of pi at infinity is also determined in a way you can describe by conjugating the complex embeddings, but I don't want to get into this. Okay. Sorry? Sure, yeah. That's a very old theorem.
No, I mean, for this, A and B are not so old.
A?
Zeros and B are not so old, but F is still arbitrary. Yeah.
Sure, yeah. You know this. I mean, okay. Okay, so let me just not write, but acknowledge that several earlier results were known, okay, about this problem, in particular by work of Meglin and of Arder Raghunathan. Okay, but Arder Raghuram, I'm sorry, and I'm not going to go to say that each time. And again, I insist the point here is to consider F arbitrary. So let me complete the definitions. But later, I will be vague. I will not always give all the conditions, but superregularity. So in the case of the Rankine functions, you have pi, which gives you some exponents pi. You have rho, which gives you some exponents qj. And the superregularity, and I have already defined, so I'm sorry, this is not what I want to do. What I want to do is define disjointness. And it turns out that this is what you want to have. You want to have that pi plus or minus 1/2 is different from qj for all ij. Okay. Okay, so as I said, it's something about the non-interference of the Roche structures. Okay. So again, my point here is to show to you how it works. And this will be easier if I take the simplest theorem, namely theorem B. So part 2. No. Before that, I have to jump because I said I would announce all the results. And let me move at some other cases. And here there's something particularly fun which comes up. Okay. So now I'm going to consider so far all representations are self-dual. Pi symplectic are even, so GLR and R even as before. And suppose that rho is orthogonal and T is also even. Okay. So symplectic orthogonal, I mean, this you can read in Arthur's book. I mean, basically, the representation being symplectic means that the potential representation of the Langlands group or the Motivig-Galois group should be symplectic. And in the same way, orthogonal. Sorry? Yeah, sure. Just like here. Yes. And orthogonal means that the representation should be orthogonal. Now, because of what I stated here for the parameters at infinity, you cannot at the same time for T even be orthogonal and be cohomological. That it doesn't fit, okay? It's the translation by 1/2 here, which forbids this. So the point is that, the problem, if you, sorry, I can go there? Yeah, okay. So the problem is, assume, again, we still assume that pi rho and are self-dual. And as I said, I mean, rho cannot both be orthogonal and satisfy the algebraicity condition, okay? And then A of rho does not exist. Of course, you could form A of rho f, but it will not be the finite component of a cuspidal representation. So I guess I can send this up. Yeah. Okay. So what can you do? Well, there's a wonderful solution in this case, which I'm going to apply to rho. So definition. I'm going to call, to define A tilde of rho to be equal to A of rho twisted by 1/2, okay? And then I untwist. In other terms, I twist back by minus 1/2. So from now on, if pi is cuspidal, pi of S is a pi determinant to the S, okay? Now, first of all, in this case, with those assumptions, rho self-dual and orthogonal, and T even, this now is algebraic, okay? So this makes sense. And this, okay, again makes sense, okay? So you have a representation of the same type, okay? And moreover, it is now, it's also self-dual. So fact, first of all, A tilde of rho is orthogonal again, and it is self-dual. You can check that easily on this formula. Okay, so now we can give the third theorem, theorem C. I'm sorry if the statements always look the same, okay? So assume the regularity conditions. Plus I assume that I am in this situation. So call this star. I mean, star is just the data of these two representations. Okay. Then again, for any A, we have L of 1/2 pi cross rho equal to 0 if and only if L of 1/2 pi A of pi cross. So of course, I have to use now my new definition for the twist, and I have to consider A tilde of rho. Okay, that's the only thing that makes sense. And if we have 0 here, then we have 0 here. So personally, I find this new way of twisting things very, very nice, and it's likely that it should occur elsewhere. When I say very nice, it means that it's probably an idea of one of my younger collaborators, but okay. And then I have to move to the last result, actually, which is a little more complicated. And that is the unitary case. Okay. So let me state one theorem. There are others. So now I assume that I have a quadratic extension A over F of number fields. Before somebody asks, let me just point out, I don't assume that this is a CM of a totally real extension. There is no condition on the fields. And assume that pi and rho are conjugate self-dual representations of GLN of the big field and respectively GLR again of the big field. I said the big field, I'm sorry. Okay. Now, conjugate self-dual means that it's not self-dual, but it's self-dual after you conjugate by the Galois automorphism. Okay. Okay. So we can consider the Rankine function in this context, L of S pi cross rho. Okay, which is explicitly L of S pi cross rho and associated to the representation standard N tensor standard R dual of the dual group. Okay, and these are L functions over E. Okay, and then I want to state again a result of the same type in this unitary case. I suppose I can. So let me state the next, the last of the results actually. So I will list some conditions. Now the unitary case, first of all, relies on the work of Mark, and two, it's not surprising, it's a little more complicated than the simply self-dual case. So I'm not going to make everything explicit. So first of all, there is regularity and disjointness. Carefully formulated for things which are conjugate self-dual, but I'm not going to write it. And then if pi is my representation here of GL NE, I guess. Yeah, GL NAE. Okay. Then there is a coefficient eta of pi, which is plus or minus 1, and which is the unitary analog of the sign, the parity of a self-dual representation. The self-dual irreducible representation can be symplectic or can be orthogonal. And in the conjugate self-dual, you have the same kind of definition, and that gives eta of pi, okay? For people who like assi L functions, which I'm not going to define, but one means that L of S of pi assi plus has a pole, which of course is familiar when you think of the non-unitary cell duality. Okay. Okay. So now let me, so I suppose I'm not allowed the bottom here. Let me go on with the last condition. Okay, so assume n plus r is even, and pi of 1/2 is algebraic, and what else do I want? And rho is algebraic. So the definition, the notations are like here, okay? And so then we can form L of S pi cross pi, the Rankin-Selberg L function. And this is L of S assi plus times L of S assi minus 4 pi. Okay. So here we have an L function which is of degree n2 over e. This is of degree n2 over f. This is of degree n2 over f. Okay. So I want also to assume that eta of pi, which are more or less defined there, is equal to -1 over r, and eta of rho is -1 over r plus 1. Okay. And then we have the rationality result. So theorem D. I suppose there's a trick for using the 3 boards, but it's too complicated for me. Theorem D. So the assumptions are in force, okay? L of 1/2 pi cross rho. These are just Rankine L functions over the big field, over E, okay? Is equal to 0, if and only if L of 1/2. So again, now this nice twist comes in, A tilde of pi cross A of rho is equal to 0. Okay. So eta of pi. And moreover, yes, there are other versions, but in this case, I assume that if eta of pi is -1 over r and eta of rho is -1 over r plus 1. They have to be distinct. Okay. Okay, that's it. So I cited the results. And, oh, so I still have half an hour, is that correct?
15.
What? 15? Okay. So I want to give an idea of the proof, and I'll be able to do that only for theorem B. So notion of proof. As I said, this takes us back to the origins of the theory with Langlands and Shahidi. So idea of proof. So as I said, I'm looking at theorem B, okay? So under our assumptions, pi is cohomological and R is even. This implies that in the terms of Arthur's classification, pi is symplectic. It actually comes from the symplectic group. And this implies that if you form it's equivalent actually to saying that L of S, lambda 2, and pi has a pole at S equal to 1. Okay. Now, consider G equal to the group equal to SPR over F. I have the French notation. So R is the rank. The group is in GL2R. And assume that R itself is equal to 2n. I have assumed that R was even. Okay. So G contains a parabolic P equal to Mn, and with M equal to, or isomorphic to, GLR. Okay. The dual group maybe I'm too low here. Anyway, I'll just finish my line. G hat is SO of 2R plus 1 and C. Okay. So we consider the unitarily induced representation. IS, sorry. G. This is GLR, it's the Levy subgroup. I think that's correct, yes? Yeah. R is even, okay, but this is GLR. It's, what's the problem? Okay. Okay, so so this defines in this situation pi, the representation of M defines an induced representation, okay, and which I'm going to write as follows: IS equal to the induced representation from Mn to G of pi of S. Pi of S I have defined before, okay? And this is the adelic induced representation, the representation of the adelic group. Okay. Now there is a lemma here, which is that for S equal to 1/2, this implies that IS infinity, the Archimedean factor of this induced representation, has a regular integral infinitesimal character. Okay. Okay, so that's just a computation. And now we fix S with a large real part. And we consider we have the Eisenstein series E of f s, okay, for which I will not write the formula, but it's an automorphic form, okay, on G of f. Remember, G is the symplectic group, and of course, G of f mod G of a, and here f is a vector in this induced representation. Okay, so we take, first of all, f equal to tensor all places of f of fv decomposed. Okay, and moreover, I assume that fv is unramified, is the unramified vector for v not in some finite number of places. Then we can write the constant term of this Eisenstein series, and the constant term, the constant term now is, of course, given by Langlands' formula. I take the constant term with respect to the same parabolic P from which I am inducing, okay? And then evil Fs, constant term with respect to P, is just F. And then there are the usual intertwining operators. So first of all, I write the part which is very simple and to understand the point of view from the arithmetic point of view, I'm sorry. Ls of 2s and lambda square, okay, by the same, divided by the same thing where I replace s by s plus 1 and 2s by 2s plus 1, okay? And then there are a number of things which occur here. In fact, the non-normalized intertwining operators, okay? And that's it, okay? So here we are in IS, and for S variable, we are here in I minus S, okay? So if you want to use that formula, the same thing, the first thing you have to do is to normalize it. And this was indicated by Shahidi, of course. We have to use the normalized operators. I have operators MV here, and I replace NV by NV of S, normalized, okay? And this is MV of S multiplied by a corresponding quotient, QV of S minus 1, and QV of S is what is missing for the complete expression of the L function here, namely LV of S pi, LV of 2S pi and lambda square, and this divided by the same thing translated, 2S plus 1. And then there is a product of two epsilon factors, but I don't care because epsilon factors never vanish and are always defined. Okay. Okay. So if you use that formula and you know a few things about the normalized intertwining operators here, a few non-obvious things, but which were obtained over the years by all the people I quoted, okay? Then you see that the intertwining operator part, the finite intertwining operator part has no importance, and that you will have a residue at s equal 1/2, exactly if the residue comes from the completed L functions here. So for S equal to 1/2, so assume, for example, to be clear, that I have a residue. So assume that L of 1/2 pi is different from 0. Then you get a residue for the Eisenstein series at S equal to 1/2. Okay. Okay. I know you have to put on your shirt and tails, and I will just sketch the next arguments. Okay. So first of all, you get a residue, but we have seen that at infinity, we had a representation which was cohomological. Cohomological means rationality properties, okay? So we have a fact here, and first of all, the residues contribute a representation in the discrete spectrum in L2. Let's say there are several such representations, but I choose one. So this will be in A2 of G of F mod G of A, okay? First of all, and at infinity, this is cohomological because we have seen what the infinitesimal character was. Okay. So we are actually in H2, the L2 part of the cohomology, which is the space of harmonic L2 forms. Okay. Now there is a fantastic theorem, which, by the way, 20 years ago and for Hermitian symmetric spaces was called the, Zucker conjecture, but it's actually true without having a Hermitian structure. That's a fantastic theorem, and this is due to Nair and Lai, I think. Just a minute. Yeah, Rai, I'm sorry. The fantastic thing is that this space is actually defined over Q. Okay, it looks miraculous to me, but H2 is defined over Q. Okay. So now I can finish the proof in 3 minutes and a half. Okay. So from pi G, we get a cohomology class in this space. Okay, for which the Hecker eigenvalues, of course, will be determined by our inducing representation pi. So I have pi G. It comes from the representation pi of GLN. And this determines completely, of course, the Hecker eigenvalues. And it's almost obvious now that, first of all, because this is defined over Q, I can consider A of pi G, or to be more rigorous, more correct, at least the finite part of this. And this obviously will be obtained by the same yoga from pi, A of pi. Okay. And A of pi, this was a residual representation. And A of pi is not cuspidal. Sorry, A of pi GF is not cuspidal. It's not cuspidal because the cohomology of pi G restricts non-trivially to the boundary of the Borel-Serre compactification. This has been known since Harder and Schwärmer. And this restriction is defined over Q, so you obtain that the same thing is true for A of pi G. And then you find that it has to come from a residue, okay, a residue for GLN. And you find that it has to be a residue exactly of the same type, namely same parabolic, and the representation pi, which pi is replaced to A of pi. So now we are almost done, okay? We look again at the canonical formula here, okay? And we see that we have to have a residue, okay? We have to have a residue because we have a residual form. And just by knowing that the intertwining operators here are actually holomorphic, 0 or not, it doesn't matter. They have to be holomorphic, but Freidun knows that, okay? And then you know that the pole can only come from this part of this expression completed by all the factors, okay? And this implies that, conclusion, at 1/2, L of 1/2, A of pi has to be, I have assumed, different from 0, I hope, and then it's different from 0, okay? Now, with different ambient groups and more delicate arguments at this point, where we have to improve on the estimates for the intertwining operators of all of these people I quoted. And by we, I mean Taibi and Valsburger, okay? Improving on these estimates so we can reach 1/2. Then the same argument replicates in all the cases.